Good morning, everybody. Appreciate you guys coming in and hearing our stories about lightweight concrete and internal curing. And my presentation this morning will be a discussion about how lightweight fine aggregate was used to provide internal curing in which reduced cracking and extended the service life of a bridge down in southeast Georgia, near Savannah, Georgia. The fort itself is an interesting project. After the War of 1812, the U.S. began construction of numerous fortifications up and down the coast to protect from foreign invasion. And this particular bridge, this particular fort began construction in 1829 to protect the port of Savannah. Wooden piles were driven 70 feet in the mud, and 11-foot thick walls were built to make the walls of the fort. And after all these old forts that were built after about 1816 most of them are still in existence up and down the Atlantic coast and the Gulf Coast. But my presentation is not on the fort, it's on the entrance bridge to the National Monument. The original bridge was built in 1938 after the War Department the U.S. War Department owned all these forts, and after this amount of time they were getting in disrepair. They wanted to get them off of their books, and so they declared them national monuments, and they turned them over to the National Park Service. The original bridge was wooden piles driven through in the river, and with a concrete deck. Had like 64 spans, all of them 20-foot spans, except for one main channel span that was 40 feet with steel girders. The entrance bridge is about 11 miles from downtown Savannah on US 80 on its way out to Tybee Island, and it's the only vehicle access onto Cockspur Island, where Fort Pulaski's located, and also there's a U.S. Coast Guard station there on the Savannah River side of the island. The bridge only, after about less than 30 years, had to be rehabilitated. I don't know the extent of the rehabilitation in 1965, but then in 1996 and 2008, there were other repairs that were required. They were contracted. Primarily, it was putting fiber-reinforced polymer jackets around the wooden piles and filling them with epoxy grout to encapsulate the timbers and make them last longer. Oops. The National Park Service and the Federal Highway Administration considered a range of alternatives to either replace or to rehabilitate these bridges. And after an environmental assessment study in 2013, they decided to replace this bridge. In April of 2015, I received a call. I'm the territory manager for Georgia and Florida. And so I got a call from Michael Dallaire, who is a division materials engineer at the Eastern Federal Lands Highway Division. And he had questions about availability of lightweight fine aggregate. He told me that one of the alternates that they were looking at on replacing the bridge had included internal curing in the bridge deck. And so I tried to answer his questions, and at that time, recently, right before that time, the ESCSI, the Expanded Shell Clay and Slate Institute, had just put this internal curing calculator on its website, and this calculator can be used to determine the minimum amount of lightweight fine aggregate that's required to provide internal curing for concrete for a concrete mixture. That calculator was based on the Dale Bent's equation. Dale Bent's worked at NIST and had done a lot of research, and all of the subsequent research since Dale came up with this formula has confirmed that to replace a little bit of the lightweight fine aggregate or the normal weight fine aggregate with enough lightweight fine aggregate to provide an additional 7 pounds of water per 100 pounds of cement is the way that you provide internal curing. And so I pulled that based on the information that Mike Dallaire had at the time. I pulled that equation up and plugged in the absorption and the desorption numbers from work that the guys at Purdue had done at the time, and I told Mike that he needed to put in at least 535 pounds of our material, which has a lower absorption than some of the other materials that would require. So you'll see internal curing projects with significantly less than this, but this was because of our material, specific material. So he would have to put in at least 535 pounds to provide enough internal curing. In 2017, the contract, the construction had started in, I think, November of 2016, and by the time the ready-mix producer submitted this mix design, it's kind of interesting. I'm not real sure why they put 35 pounds of silica fume in this mix, but this was we kind of backed off on the amount of strength, compressive strength in bridge decks, but they wanted a 5,000 psi concrete for the bridge deck with 465 pounds of cement and 106 pounds of fly ash, and then of course 35 pounds of silica fume. So it turned out that, as you can see, they included. Let me see if I can find the number now. They included 564. I'm sorry, it's highlighted right there. 564 pounds of lightweight fine aggregate in this mix design. So the new bridge was 1,295 feet long. It was constructed 6 feet to the west of the old bridge, and with concrete piles, cast in place pile caps, and pre-stressed, precast girders with cast-in-place diaphragm walls and abutments walls. When they began construction of the actual bridge deck, the plan was to use a boom truck and work off of the old bridge with one-lane bridge closures. And but we've seen this over and over again, where the boom position with going straight up and then coming straight back down, you can have significant slump loss and air loss. So they kind of went back to a 3 cubic yard bucket, and this provided ample production. They were satisfied with their progress. So they did all 13 of the spans on this bridge using a 3 yard bucket. And about 900 yards of concrete, internally cured concrete. The bridge is the new bridge is 29 feet, about 29 feet wide, including the rails, to 11-foot lanes and a 5-foot shoulder on the downstream side. There was one incident of plastic shrinkage cracking out of the 13 pours. What happened was, in the very first pour, when they left, the curing mats and polyethylene blew off and exposed a small area. And they did have one shrinkage crack in that area. And of course they started taking more care with their curing mats after that, and they didn't have any other episodes of plastic shrinkage cracks. They did a crack survey, and about 4 months after they completed all of the 13 spans, which was about 7 months after this this deck, and they realized that they didn't find any other cracks after 4 months or after 7 months. I didn't realize they were doing these crack study or crack surveys, and so I sent Mike DeLaren an email to ask him if they were satisfied with how the project had gone, and this is his response. This is his email. It said that the Fort Pulaski Bridge was a success from our standpoint. We had around 4 linear feet of cracks for all the multiple placements, which totaled about 900 cubic yards. So these were plastic shrinkage cracks, no drying shrinkage cracks as of a year later. So very pleased. Well, shortly after they sent this, at 14 months, they did another crack survey, and they did find an additional 3 feet of cracking in the second span. But total, this is 7 feet of cracks, cumulative. They did another survey at 28 months and found some small cracks that radiated from the joint at the 11th span. And so a total on the whole bridge was, if you add all the cracks up, was about 10 feet. And 10 feet for cumulative cracks for a 35,000 square foot bridge deck is not bad. And of course, after the new bridge was finished, the old bridge was demolished and removed. And in all the years that I've been in the lightweight business and in the concrete business, we've observed that lightweight concrete in bridge decks and in other applications just lasts longer than normal weight. And so, over the last 30 years, there's been a lot of studies on internal curing, and that have proved that internal curing targets and mitigates the cause of these cracks. The Fort Pulaski National National Monument entrance bridge is just one example of how lightweight fine aggregate internal curing can extend the service life of a bridge by reducing the cracks. So that's it. Yeah. Maybe I'll make up a little time.